All right, guys, we're back. Now, last time we were talking about how if we do a regular average, we end up with calculating out 2 grams per mole for the atomic mass of hydrogen, taking into account all the isotopes of hydrogen. However, again, when we looked at the periodic table, we find that the actual mass of hydrogen is 1.00794 grams per mole, a significantly lower difference. And the reason for that is because we don't use an actual average, we use what's called a weighted average. What this means is we actually have to take into account something called percent abundance, or you'll also hear relative abundance. In other words, what actually shows up in nature for us. Now, this wonderful looking little equation here can actually be broken down pretty easily. What this means is this is the sum of the mass number and percent abundance times the percent abundance of each isotope, and then we're going to divide that by 100. Warning, the division by 100 is dependent upon if you follow the method I use, okay? So be careful with this, as there are a couple different ways of doing this. And I'll explain why I like this method above the other one. So the first thing, so what we're going to do is we're going to take the mass number of our first isotope, our mass number, 1. We're going to multiply that by the percent abundance. So we come mass number, percent abundance, 99. That's our first isotope. You'll notice I did not change the percentage to a decimal first, okay? I don't do that for a reason, and I'll go over after I finish setting this up for you first. Percent abundance. Now, since it's a sum, that's not the only isotope. There's 2 more, so I'm going to add to it the second isotope, 2 times 0.99. Again, it's a sum of all of them. There's a third one, so I'm going to add in the mass number times the percentage, 0.01 of that. Now, I've got all the isotopes. Top part's done. I'm going to divide that by 100. Now, when I do that, I end up with 1.0101. As you can see, it's a little bit off, but if we were to round both of these to the hundredths, we would end up with 1.01 grams per mole if we rounded them both to 3 significant figures. All right, now, why do I not first convert the percentage to a decimal before doing this? Because each time you manipulate a number, you run the risk of making a very easy, simple mistake. Either moving the decimal too far, not moving it far enough, but I like to eliminate those potential errors. So what happens is by taking the numbers directly from your chart, like what I have up here in this case, and putting them into here, it's real easy to check. 1 times 99, 1 times 99, 2 times 0.99, 2 times, and then 3 times 0.1. So it's easy to double check. Secondly, by dividing by 100 at the end, I take care of all 3 decimal conversions in one go, one step. All right. Again, it eliminates a lot of potential for error, so that's why I like this version of the formula versus other ones that you're going to see like in a book where you have to, you're basically doing the same thing except you're converting the decimals first, then adding them up. Okay? Again, choose the way that works best for you. But again, this is my reasoning for this. All right, now, how do these show up in actual problems? Let's take a quick look. Here's where it's really nice, okay? I've seen people do this in multiple ways, but I'm going to walk you through. Here, you're given a chart. You've got every single isotope. you got the masses, you got the relative abundance. You got everything you need to calculate out the average atomic mass in a nice chart. We love it when it's like this because we don't have to do any more extra work. All right? So we got 3 isotopes, so that means we're going to take our mass for the first one, 19.99 times 90.51 plus, because remember, it's a sum. Remember, we're summing up, okay? That wonderful little sigma there. Next isotope, 20.99 times, because remember, that's what the dot stands for, 0.277%. Third isotope, again, keep going, plus 21.99 times 9.223. We're going to do that whole thing, then we're going to divide by 100. Once again, guys, it makes it nice and easy as we go through. We don't have to do any extra work. It's all given to us here. So when we do this, we get 19.99 times 90.51 plus 20.99 times 0.277 plus 21.99 times 9.223, and we're going to divide that by 100. And what you end up with is, well, when we round, you end up with 20.18, and remember, this is grams per mole. Okay? So when you're given a chart like this, where you have mass and you have relative abundance, setting this up is nice and easy. You just take this number times this number, then you add it, do the same thing for each line, add them up, divide by 100, and you're done. So what do we do if we're given it in word form? I know how many people love word forms for atomic masses. Well, do the same thing, except here you've got to create your own chart. So you got to be a little bit more careful and make sure you're matching up your numbers correctly. All right? Don't let the wording confuse you. Again, as I like to say, go through, pull the necessary information. All right? The first thing it's going to tell me exactly what to do right there. I want the average atomic mass. That means I'm going to use my wonderful little formula. So that's that sum formula, okay, of mass number times percent abundance. Again, I like to divide by 100. All right, so now I got to find out how many isotopes. I got to find out, get all that information. All right, so here's where we go through. We look. So chlorine has 2 common isotopes. Here we go. 35Cl, 37Cl. So we got chlorine 35 and chlorine 37. All right, now the next thing I need to know, because I'm looking for atomic mass, is I got to know their percentages. Okay, so, well, we have an abundance. Okay, so we got a percent here and a percent here. Keyword is respectively. Respectively means in the same order as they were given above. So that means chlorine 35 is connected to the 75.53%, and then 24.47% is connected to chlorine 37. Okay? We've got all of our numbers. We've got all our percentages now. All right? So that means we can now set it up. So we're going to take 35 times 75.53 plus 37 times 24.47, and I'm going to divide that all by 100. That means my final answer is going to be 35.46 grams per mole. All right. Now, let's see, what was I going to say? Again, I I like doing it this way because while the problems I did here only have like 2 and 3 isotopes, there are some elements out there that have 30 plus isotopes. Again, so going through and calculating that can be a right pain, so you've got to pay attention to your details. Again, dividing by 100 at the end is really nice because it takes care of every single percent conversion, percent/decimal conversion, and does it all at one time. That way you have a tendency to make fewer mistakes. Anyway, I really hope this helps, and I look forward to seeing you in the next episode.